Okay, so we are going to uh, learn how to solve systems of equations in three variables. So in the previous section, we had intersections of lines, just two lines in two dimensions. If we add a third variable to picture this, it's going to be in 3D. So there's a bunch of different possible scenarios that can come out of this. You could have A here. You could have, so for this first picture, A, you can have a single solution where, so we're thinking of like 3D, so we're thinking planes. You can have the intersection of three planes that intersect in exactly one point, and that is going to be an ordered triplet x, y, z. So instead of just x, y, an ordered pair, it's an ordered triplet. You could have three planes that intersect in one line, like B, in example B. You could have three planes that are all exactly the same plane, and that would be an infinite number of solutions. A, B, and C are all infinite number of solutions there because they have, or no, the first one is just a single solution, but points on a, if you have points of a line that are in common for all three planes, which are going to be equations in three variables, you would have an infinite number of solutions. Here you would also have an infinite number of solutions. Any point on the plane is on all three planes. You could have a scenario, so think of like stacking papers. You have parallel, a piece of paper kind of represents a plane, but a plane goes on forever in every direction. But if you just had three planes that never intersect, so I don't have three hands, but imagine a third one there. You have no points in common. You can have two planes that are parallel, so 1 and 2 are parallel here, and 3 intersects both of them, but there are no points in common for all of them. And same thing with this last case right here, no points in common for that situation either. So you guys are going to get three equations with three variables, and you're going to have to decide what type of system it is. So pause the video and write down the types of solutions for solving systems in three variables. So if you have the solution set for a system of three linear equations in three variables is the set of ordered triples or triplets that satisfy all three equations. It doesn't have to be these variables, but generally, like for the problems we're going to do, it's going to be an ordered triplet x, y, z. So you have to put it in that order. If you solve for x and y and z, you have to put it in that order for your answer. And you'll get an ordered triplet when you have one point in common. If the second scenario, if three variables are eliminated and we are left with a true statement, so this is important, if you are left with a true statement, all the variables disappear and you end up with something like 0 equals 0. That's a true statement. That system is going to be considered to be dependent, and you have an infinite number of solutions. The third case, with a system of three equations in three variables, a dependent system has an infinite number of solutions. So dependent systems, infinite number of solutions. And then the fourth scenario, if three variables are eliminated and you're left with a false statement, then the system is inconsistent and has no solutions. All right, so inconsistent is if you end up with a false statement. Dependent is if you end up with a true statement and all the variables have disappeared. Okay, so here we go. We're going to solve our first system. You need to make sure that you have enough room on your paper because these get pretty long, and you have to be methodical and neat with your work. You have to keep track of your work here. So stop and write this system down. So what we're going to do first is we want to eliminate one of the variables, just like we did in 10.1, where we solve systems with two equations and two variables. We're going to pick a variable to eliminate. And so you look at the coefficients of all of these systems here. So equation 1 has coefficients for x, y, and z, and remember coefficient is the number in front of the variable. We have a 1 and a 1 and a 1. And they're not written there because you don't need to, we don't usually write ones if it's just a 1 in front. So I'm going to get rid of that. But just remember that it's 1x plus 1y plus 1z. In equation 2, we have 1x minus 1y plus 2z. And then in equation 3, we have a 1 and a negative 1 and a 3. So which one would be the easiest to get rid of? I'm going to say let's eliminate y. And that is not the only choice. I wouldn't try z though. It really doesn't matter. These numbers are pretty easy to work with. But sometimes it will make it harder or easier depending on your first choice here. So I'm going to say let's eliminate y, and I'll show you why I'm doing that. Okay, so I'm going to take, if I take equation 1, and I like to label my equations, you guys are going to not want to, you're going to want to have scrap paper to do these problems before you input your answer. But label the equations 1, 2, and 3, and we need to keep track of all of our different equations. So if it's an equation that I'm trying to keep track of, I put it in a circle just so I don't think it's a coefficient or something. All right, so if I take equation 1 and just write it here, x plus y plus z equals negative 4, and then I write equation 2 right under it. The reason I chose y is because if you look at what's going to happen here, oops, that's a 2z equals, you don't want to make sure that you're writing things clearly. I always put an extra bar through my z so I don't think it's a 2. That's a good thing to have it to be in, I think. Okay, so if I add these equations right now without doing any other work, I'm going to end up with 2x here. So the columns, you're going to add each column, and they're like terms, so you can combine them. But notice what happens with the y, it gets eliminated, and that's what we're trying to do, is eliminate one of the variables from 2 of the equations. 1y plus or minus y equals 0. You don't need to write the 0, you can if you want. And then I have plus 3z equals negative 4 plus 1 is negative 3. So now I have another equation. I'm going to call it equation 4. 2x plus, I'm not going to write that 0, plus 3z equals negative 3. So now what you're going to need to do is you're going to need to pick 2 more equations and eliminate the same variable. You want to eliminate y again. So you have to use equation 3 because we haven't done that one yet. And notice that this is a negative 1 in front of that. And equation 1 has a positive 1. So again, I can just write these down and the y's will drop out. So I'm going to take equation 1 again. And equation 3. And it won't always be so, it's not just going to be that they're just going to drop out. You're going to oftentimes have to multiply by something to get them to be exactly the opposite, like we did with 2 systems of 2 linear equations and 2 variables. So add down, you get 2x, and then the y minus y adds to 0. I'm not going to write it this time. 1z plus 3z is 4z, and that equals negative 6. I'm going to call that equation 5. So equation 5 and equation 4 are now 2 equations with 2 variables. So now I can go back to what we were doing in 10.1, and I can solve for either x or z. I can eliminate x or z, and then I'll have one of my variables solve for, and then I can sub that back in to equation 4 or 5, and then those 2 variables back into equations 1, 2, or 3. So follow along here. I have equation 4, 2x, so the coefficient in front of the x is 2, and the coefficient in front of z is 3. And if you look at equation 5, I've got a 2x and a 4z. So if I take equation 5 and I multiply it by a negative 1 and write it right underneath equation 4, the x's will be exactly the opposite, because this will be a 2, this will be a positive 2x, and if I multiply that by a negative 1, it's going to be a negative 2x. My x terms will drop out, which is what I want. So I'm going to multiply every term here by negative 1. So that's negative 2x minus 4z. It just changes all the signs. Equals positive 6. And then I'm going to add negative, I'll go left to right. 2x minus 2x is 0. You don't need to write it. 3z minus 4z is a negative 1z. And then the constants over here, negative 3 plus 6 is 3. So I've almost solved for my variable, but I have a negative z equals 3. So to get rid of the negative, and that 0, we don't even need that there. I'm just going to erase it. So we have negative z equals 3. Divide by a negative 1, because it's really like a negative 1z. Divide by negative 1. The negatives cancel out, and you get z, I'm going to write it over here, equals 3 divided by negative 1, which is negative 3. Put a box around that so you can keep track of that. Now we have our value for z, and we can take equation 4 or 5 and plug z into either one of those, and we'll be able to solve for x. So I'm going to just pick equation 4. That's just because it doesn't matter. Either one will work. But if I pick equation 4, oops, and I plug in, I'm going to plug in negative 3 for this z. So I have 2x plus 3 times negative 3 equals negative 3, and now solve that for x. So I get 2x, 3 times negative 3 is minus 9 equals negative 3. Add 9, and I get 2x is equal to 6 divided by 2, and you get x equals 3. Put that in a box so you can keep track of it. Now we know x and z. Now I can pick equation 1, 2, or 3, and I'm going to pick equation 1 because it's all positive numbers, and I'm going to plug in 3 for x and negative 3 for z. So I know x and z. So 3 plus, I don't know y yet, and then this is going to be minus 3 because z is a negative 3 equals negative 4, and then solve that. So 3 minus 3, add the terms on the like terms on that side, adds to 0, so I get y left on that side equals negative 4. And I am done, except for you should check your solution. My solution to this system is an ordered pair. Remember, no, it's not an ordered pair. It is an ordered triplet, xyz, and it equals 3, negative 4, and negative 3. So you could try that in all of these equations to make sure that it is true. I'm going to stop here and do another video with some different types of examples.